Okay, so I will rebooting my laptop. Okay, so did you watch the recorded video? Okay, everyone watched the recorded video, right? Okay, so actually in the previous class, so so I posted the recorded video, and then so in the previous class, so we learned about some additional RISC-V instructions, right? So and in this class, so we will learn about the conditioner. So I'm rebooting my laptop. Sorry about that. So what are conditional instructions? So actually in our, so when you write a code, we frequently use if else statement, right? So actually we frequently use the conditional statement. So actually, so in the if else statement, so if else statement includes some conditions, and then if the condition is true, then we can execute some statement. It's a true statement. And then if the condition is false, then we can execute the false statement. Okay. Okay, so oh, it's not working. What happened? Oh, it's working. Okay, so now it's working. Oh, okay. No problem. Ah, so it's so complex. It's so annoying. Yeah, so I believe you. So finally, you can see the slide deck. So, in order to okay, sorry about that. So, in order to support the conditional statement, so RISC-V instructions also include conditional branches or jump instructions. So, and then these instructions are called branch instructions. So, actually these instructions are very important instructions. So it is because, so as I mentioned, we frequently use conditional statement in our program. And then, so using this conditional statement, we can write very fancy very fancy code. Okay, so in order to support these statements, the conditional statement, the RISC-V includes branch instructions and jump instructions. Okay, so we can categorize the branch instructions as the two types. So conditional. So as I mentioned, so this is called the conditional branch. So conditional branch means that based on some conditions, defined conditions, then the branch can be taken or not taken. So I use the word taken. Taken. So taken means that the condition is true, is a true condition. So the branch jumps to the target of the branch. Okay, so it jumped to the target. So not taken. Also, if the condition is false, it's called the not taken. Okay, so it's a condition is false. So then in this case, the branch does not jump to the target. Instead, the branch just execute the next instructions. So we learned how computers execute instructions, right? So computers just execute the next instructions sequentially by changing PC values. But we already know that. So I believe you are doing the lab assignment. So actually, if you if you already did the lab assignment, then I believe you can find the PC is just increased, right? So by increasing this PC value, then the computer just fetch instructions from memory, and then these instructions are executed sequentially, okay? Sequentially from top to bottom. So, but the branch changes this execution path. So I mentioned that the conditional branch has two cases. It's a taken case and not taken case, right? Based on the condition of the branch instructions, okay? Also, the RISC-V has unconditional branch instructions. So these instructions are also called jump instructions. So, okay, the jump. So unconditional branch instructions do not have conditions, okay? It just jumps to the target, okay? So there are two types of branch instruction, conditional and unconditional, okay? So, and then, conditional branch instructions, we can define the condition of a branch, condition of this branch instruction. So you can find these four instructions like BQ, BNE, BLT, and BGE. So it means, so BEQ, so it starts with B, it represents branch, right? So BQ represent branch if equal. So it's called BQ. So BQ just compares the two values A and B, and then if these values are equal, then it means the branch condition is true. And then if the branch condition is true, then it's taken case. So the branch instruction includes the target. Okay. So target means the actually target PC. So program counter. Okay. So I will explain later. Okay, about this target PC. So so you can find that this PQ just compares two values, and then if the two values are equal, then the condition is true. So you can find the B and E. So you can find the representation, the meaning of the B and E. It's branch if not equal. So NE. And then BLT means is less than. Branch if less than. And then BGE means the branch if greater than or equal. Okay. So less is this one. And then greater than or equal is this one. Okay. Okay. So you can find some very familiar conditional operators in C. Okay. And then unconditional branches. So it's also called jump instructions. It jumps to the only target of this jump instruction. It's a branch instruction. Okay. And then these instructions do not include conditions. Okay. It just include target. Okay. So you can find the jump and jump register, and then jump and link register. So these instructions are used for function calls usually. Okay. So learn about these jump instructions later also. Okay, so let's see the example of branch instructions. So you can find these example instructions, the example assembly code. So where is the branch instruction? So you can find the BQ. Okay. So BQ instruction is here. Okay. And then what are operands of BQ instructions? So you can find that S0 is general purpose register, right? And then S1 is here. And then also you can find the target of this BEQ. So as we learned, so so we learned about the meaning of BQ. It's the branch if equal. So BQ just compares the values in S0 and S1. Okay, so this is the conditional operator in C. Okay, so if the S0 is equal to S1, then it's true. And then if it's not equal, it's false. So if the branch condition is true, so what happened? It's true, then it jumps to the target. So it jumps to the target. But where is this target? So you can find the target label here, right? So so in the assembly code, you can find some labels. So this is called a label. And then so actually this label indicates the target of branch instruction. So you can find that target of branch instruction is, so it's a name of a target of branch instruction is target. And then you can find the label target here. So if the branch is true, if the branch condition is true, then it jumps to the target, right? And if the condition is false, then branch, the processor just execute the next instruction. What is the next instruction? This add I. Okay. Then how does a branch jump to the target? How? How how can a branch jump to target? So we learned PC. PC is the address of an instruction, right? So it means that so it jumps to the target. Then if the branch jumps to the target, then this instruction will be executed. So what does that mean? Branch changes this PC value. So PC is the register. So this PC register includes the PC value of this code, right? So actually, a branch instruction, also jump instruction is also branch instruction change PC register, okay, to the target. So if the branch does not change the PC register, then actually in order to execute the next instruction, so if this is PC value is A, then we just increment the PC value by 4. So it is because in RISC-V, the size of an instruction is 4 byte, right? So this PC value is A plus 4. So you can also observe the PC values of some generated assembly code in lab, right? So you can find that for the instructions, the differences in PC are always 4, right? Right? So the PC value is, if this PC value is A, then this is A plus 4, this is A plus 8. Okay, so in order to execute the next instruction, we just increment the PC value by 4, right? But branch, if the branch condition is true, then branch just change this PC value as the target of a branch instruction. So which means that if this target value is so it's a plus 12, 16, 20, and 24. So it's a plus 12, 24. Then branch just change the pitch value as the a plus 24, right? So branch change the PC value. So by doing this, branch can jump to the target of the branch instruction. So in this example, so S1 has the 4. So S1, S0 is 4, S0 is holding 4, and then S1 is holding also 4. So which means that S0 is equal to S1. So its condition is true. So it jumps to the target. So a processor execute this instruction the next. Okay, so these instructions are skipped. Okay, it's not executed, not executed because the branch condition is true. So another case is that branch is not taken. Okay, so in this example, S1 is not equal to S0, right? Oh, it's equal. Okay, but the branch instruction is changed. So S0 is 4 and the S1 is 4, but branch is changed. It's BNE. So it represents branch if not equal. Okay. But so it just check the condition of this. Okay. So it says it checks the S0, S1, right? So in this case, the condition is false. So it does not jump to the target. Instead, the next instruction, add I, will be executed. So this is PC is A. So this is A. Why is not well? A plus 4, A plus 8, A plus 12, A plus 16. So in this case, like the ordinary instructions, a processor just increments the PC value by 4. Okay, so by doing this, the processor can execute the next instruction. Okay, this is the false case. It's a not taken case. So these instructions are executed and executed. So how about this instruction? So you can find that this is the target of the branch instruction, but branch is false, then this instruction will be executed. What is the flow of execution of instruction? So how about this? So after this instruction, which instruction will be executed? Which instruction? Next instruction, right? So what is the next instruction? This instruction, right? So I mentioned that this is the PC is it's a plus 20. So this PC is the A plus 24. Okay. So then if the branch is false, this instruction will be executed, and next this instruction will be executed, and then this instruction will be executed like the normal instruction path, right? The PC is just incremented by 4. Okay, it's a normal execution. Okay, so this label, the label just represent the target. So it represents the PC of this instruction. Okay, so you can just understand like this, or target. So this label just to represent the PC, the program counter of this instruction. Okay. Okay. So this is the example of unconditional branch instruction. So jump instruction. So if you see this jump instruction, you can find that jump instruction does not include a condition, right? Jump instruction just includes target of branch instruction. So what will happen? So if the jump instruction is executed, then this is already taken, right? It's a taken. Okay, so it jumps to the target. So you can find the label target here. So it jumps to the target. So these instructions are skipped. Okay, so this instruction will be executed after this jump instruction. Okay, so this is the meaning of behavior of conditional branches and unconditional branches. Okay, so let's see the example with the C code. So as I mentioned, we frequently use conditional statement in C. Okay, so we frequently use if statement, if else statement. Also, we frequently use repeated loop, so iterative loop, right? Like we frequently use while loop, we frequently use for loop. And then in order to implement these statements, we require to use branch instructions. Okay, so let's see the example. So this is the example of if statement. So you can find the if I equal to j. Okay, so this is the condition. Then if the condition is true, okay, then this statement will be executed, right? And then this instruction will be executed. Then how can we implement this code in RISC-V assembly? So if we just read this C code, so you can find that, if the condition is true, then, this is executed. This statement is executed. So like the add instruction in RISC-V. And then if the condition is false, then, no. So, and then this instruction will be executed. It's a solve instruction. Then how can we implement this using a branch instruction? So you can firstly think that, if the condition is true, then this will be executed. But you can just think like that. So this can be branch instruction, right? Then what is the next instruction? So next instruction will be this add instruction, right? So branch is here, so we don't know which branch. And then this is the add instruction. And then this is the solve instruction. Actually, this solve instruction will be executed always, right? So regardless of the condition of branch instructions. So actually, this add instruction will be influenced by the condition of branch instruction. And then the condition is, if the branch condition is true, it's executed. And if the branch condition is not true, it's false, then it's not executed. Okay? And then we already learned that branch has the target. And then the target of the branch instruction is not the next instruction. So what does that mean? If this condition is true, then this instruction need to be executed. So it means actually, if this branch needs to be not taken, right? So if this condition is true, then this instruction is executed. So which means that because this add instruction is the next instruction of the branch instruction. So which means that the branch instruction should not be taken. It's not taken, right? Then this instruction will be executed, right? If the branch is taken, right, then it needs to jump to this sub instruction. So which means that if the branch condition is true, then it jumps to the sub instruction. This is the skip case, right? So we need to think about this. So if we see the translated, the compiled RISC-V assembly code, you can find that BNE is used. So BQ is not used here. So if you see that this if statement, you can find, oh, this is the, so we can use, you can first think that, oh, this if statement just checks the equality, right? But actually, in order to implement this statement, we use BNE. Why? If this condition is true, so if this is not equal to S3 is not equal to S4, then it jumps to the L2. So actually, this is the worst case of this if statement. Okay, just skipped. And then if this condition is true, so it is not equal to it's equal, then this instruction is executed. Okay. So it is because, so actually, when we write a code, we write the code like this. If the condition is true, then the next instruction will be executed, the next statement, right? But actually, when this statement is implemented using the conditional branch instructions, then next instruction is the false condition of the branch instruction, right? So that's why we need to use the BNE here, okay? So if this is not equal, then add instruction is skipped. Okay, so do you understand? So this is the just the example. And then if else statement. So if else state, so we also frequently use this if else statement, right? Then how can we implement this if else statement? So it actually in this if statement, this if statement just contests the equality of I and j. And then we learned that actually when this statement is translated into the RISC-V assembly code, then we need to use the opposite condition, right? We need to test the opposite condition. So we use the BNE, okay? So BNE just to check the inequality of the S3 and S4, okay? Then if this condition is true, so which means that I is not equal to J, so it's true, then it jumps to L1. So where is L1? L1 is sub here, okay? So it will execute the F equal F minus J, okay? So because we use the B and E, but if this condition is false, so which means that S3 is equal to S4, then add instruction. This instruction will be executed, right? Also, you can find the jump here. After that, if there is not jump here, then L1 will be executed. So we need to avoid this case, right? So jump needs to be here. So what can you observe? So we can observe that. So this code just check the I equal Z, right? So if the true and false, then the plus is executed and minus is executed. Then it's converged at this point. In the next, after this if else statement, the execution path is converged. Okay. So in order to execute this execution path using this RISC-V assembly code, so we need to use the branch conditional branch, and then after this true path, then we need to use the unconditional jump. Okay, so we need to skip this instruction. So you can find that. So actually, so this is the very simple, so simple statement, right? So if we frequently use if else statement very frequently, right? But you can find that many branch instructions are actually used here. Okay. So 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 actually in a normal applications, so we frequently find many branch instructions actually. Then okay, so we will learn about the process architecture later, but so you can find that actually the branch instruction is very critical for the performance of a processor actually, because the cycles are wasted by branch instructions. Okay, but problem is that we can observe many branch instructions in our code. Okay, so that's very critical issues in the application. Okay. Okay, so this is the another example is the while statement. So what is the while statement? So in C code, if the condition of a while statement is true, then this statement under the while statement will be repeatedly executed. Okay, so then how can we so repeatedly executed? So what does that mean? So this statement will be repeated. So it means the programs will be executed from top to bottom sequentially, but repeated means that, what happened? So if the program encounters this bracket, so the bracket of this while statement, then it jumps to the start point of the while statement. Okay, this is the meaning of iterative loop in our code. So you can find that. So, this statement, this code will be executed repeatedly. So, we frequently also use this iterative loop, right? But it means it jumps to the start point of this code. So you can understand like this, okay? This is the meaning of iterative loop. So this is the example code. So we can actually, so you can find the conditional jump here, and then so you can find the conditional branch here. Okay. So after this add instruction, okay, after this add instruction, then you can find the jump instruction here, and it goes to this while label. Okay. Then condition is checked, and then if the condition is true, then it goes to done. If the condition is not true, then it executes this one. So like the previous example, you can find that. So the condition of this branch instruction use the opposite condition, so opposite case. Okay. For loop is the same. Actually, for loop also check the condition of I, right? And then for loop execute this statement. So actually, for loop is very similar to the while loop because this is the initial state, and then this is the condition, okay? And then this is the some iterative execution, okay? So I is just incremented by 1, and then sum is also use the add instruction. So when the for loop is executed, so it repeatedly execute this sum plus 1, sum plus I, then it also execute the I plus plus, okay? So actually it's very similar to the while loop. So you can find the condition here. So actually you can find that BQ is here because this is the opposite case of this I is not equal to 10, okay? But it checks the equality between I and 10. Then this is the this sum add instruction, just implement this sum, and then you can find the add I S0 S0 1. So this is the add instruction using immediate value. So it is incremented by 1. S0 is incremented by 1, right? So this is actually I plus plus. Okay. So, and then you can find that after that it goes to the start point of the for loop. Okay. So as I mentioned in the iterative loop, then it jumps to the start point of the statement. Okay. So this is the another example. Okay. So you can also find the C code and then the translated assembly code here. Okay. So another version, another version used the SLT. So SLT, so you know this is the rather new instruction in RISC-V, not RISC-V, so it's a new instruction in this course, right? So SLT represent the set if less than. So that's why it is SLT, okay? SLT, set. So what is the meaning of set? What is the meaning of set in a digital system? So set or reset. Set means it makes a certain value 1. Okay, 1 actually 1 represents the true in a digital system. Reset, so opposite. So it makes a certain value 0. Okay, so it actually represents the false. So if we just see that this instruction is a set less than, so set if less than, so it means, so if this value is, so it just compares the two values, the T2 and S0, and then if the T2 is less than S0, then it sets T0. It makes T0 1. Okay, it set. Okay, so I explained the meaning of set is it makes 0, makes 1. Okay, okay. So then also you can it's a no. Actually, SLT, this T2 is the destination, like the add instruction, and so it just it compares the S0 and T0. Okay. So because the T2 is the destination, so like the add instruction, like add x1, x2, x3. So it means that x1 is the destination of the add instruction. So x1 becomes the x2 plus x3. Okay. So like the add instruction, so SLT has the same structure. So T2 is the destination. So it sets T2, set T2 if S0 is less than T0. Okay, this is the meaning of SLT. So, and then you can find that after that, BQ just compares T2 with 0. Okay, so it means that if the S0 is less than T0, then T2 is 1. And then it means that this is false. Then it jumps the done. Okay. So this is the another version. So it used the SLT. But if we can just compare this code and this code. So actually this code, actually these two codes are equivalent code. But which is better? What does that mean? So I mentioned which is better. So which means which code will exhibit higher performance. So which code is better? So it means which code will exhibit the higher performance. So we can compare. How? We can use the equation, right? Which equation? Execution time is the instruction count multiplied by CPI and then TC. So we are learning about the software part, right? So if the CPI and then TC is the same, the hardware part is the same, then we can just compare the instruction count. We can just count the number of instructions here and here. So in here, so there are seven instructions, right? 7 instructions, but here there are 8 instructions, right? So we can say that this code is better, right? Because there are less instructions, right? And so so it may exhibit higher performance, okay? And then also you can find that in the conditional branch. So these instructions just compare two values. So which means we need to consider signed and unsigned. So actually, if we use the B and E or BEQ, these two instructions just to check equality or inequality, right? And then actually, in order to check the equality of the two values, then we can check each digit of digital values, right? We can just check the equality of each digit, right? But other instructions like the BLT and BGE, BLT just check the less than, BGE check the greater than or equal. So it compares the magnitude. It compares two magnitude of the two values, right? So in this case, we need to consider the signed or unsigned numbers of these BLT and BGE, right? So it is because in the tooth complement, the MSB is 1, but in the unsigned number, if the MSB is 1, and it means this value is a very large value. But in the tooth complement is a signed number. If the MSB is 1, then it represents this number is the negative number. It's a smaller number, right? So that's why we need to distinguish signed number or unsigned number of the BLT and BGE. But you can think that actually in default, then so the RISC-V just handle signed numbers. So if we just use the BLT and BGE, then these instructions perform signed comparison. Okay, so it compared the two values, but it just performs signed comparison. So it means these PLT and BG think that, oh, these numbers are signed numbers. Okay. So if we just compare the unsigned numbers, then we need to use the PLT U and BGE U. Okay. So it performs the unsigned comparison. So this is the example. So X22 has the all ones and X23 is the all zeros. And then if we just use the BLT and BGE, then it just compares the signed numbers. Then what is this number? This number is -1. This number is 1. Then which number is smaller? -1 is smaller than 1. So actually X22 is less than X23, right? So if we use the BLT, then BLT X22 or X23, then it's true. How about but if we use the BLTU, so it's a BLT unsigned, right? Then actually this number is the very large number, right? It's a very large. And then this is 1. So it's a very large number. So actually the condition is false. Okay. So if we just compare unsigned numbers, then we need to use the BLTU or BGEU. Okay. And then you can think that, oh, RISC in default, RISC-V instructions handle signed numbers. Okay. Like so we just in the previous class we compared LB and LBU, right? The load byte and load byte unsigned. Okay. Okay. So let's learn about the basic block. So basic block is the very important concept in a program. So in an instruction code, is assembly code. So let's see the definition. Definition of basic block. A basic block is a sequence of instructions. So it's a sequence group of instructions with no embedded branches. So what does that mean? In the middle of the basic block, this basic block does not include branch instructions, except at end, the last instruction, and no branch target, except the first instruction. So this is the definition of a basic block. So you can understand that, oh, actually basic block includes the target of a branch, is a label, target of the branch only at the first instruction, and basic block includes branch instructions only at the last instruction, at the end of the branch instruction, and at the end of the basic block. So this is the definition. Okay, so it's just definition. So it means that you need to memorize. You need to memorize the definition, right? Then why basic block is? Why do we need to learn about the basic block? So it is because we can optimize. So actually the meaning of a basic block is that if this first instruction of the basic block is executed, then we can guarantee that other instructions in the basic block can be executed sequentially. Okay, so so I mentioned that if the first instruction of the basic block is executed, so we can guarantee that other next instructions are executed sequentially. Okay, sequentially. So this is the meaning of a basic block. So actually you need to memorize the definition also. The meaning is that if the first instruction is executed, then we can guarantee other next instructions will be executed sequentially. And then actually this is very critical for the optimization techniques. So it is because compilers can, so actually we will learn about this optimization techniques later, but compilers can change the order of instructions to improve the performance of our assembly code. So we learned about the compiler optimization, right? Like the minus O0, minus O1, or minus O2. So this is optimization level of the GCC, is a GNU-C compiler. And then if we just apply the different optimization levels, then we can observe the performance changes, right? Okay. So which means using the compiler optimization techniques, we can improve the performance. So, but compilers usually, compilers can apply many different optimization techniques, but the basic optimization technique is to change the order of instructions inside of a basic block. This is the first try, okay? So it is because actually compilers can analyze the code structure using basic blocks. So for example, actually when I explain about the if else statement, then you can find that actually the execution, the program is executed like this, but at this if statement, the program execution path is diverged, right? It's a diverged, and then it's converged at this point. So actually, compiler, so we don't know actually. So compilers cannot know which instruction will be executed because this execution path is determined by condition of this if statement. And then, the condition of if statement can be changed by user data. So compilers cannot change these code structures, but inside of the basic block, compilers can change the order of instructions in order to improve the performance. So that's why basic block is critical. The size of basic block is critical for the performance of the processor. Performance. Also, actually, so if you take the advanced computer architecture course, this is the graduate level course in Korea University. But so if you take the advanced computer architecture course, then you will learn about the out of order processing. Then out of order processing means that actually the order of execution is changed by hardware in order to improve the performance. But this out of order execution is also blocked by branch instructions, a basic block. So it can be easily the order of execution can be easily changed inside of the basic block, but at the branch instruction, it's blocked. Okay, so it's critical for the performance. That's why the basic block is critical. Okay, so try to memorize the definition of a basic block, and then also understand the meaning of a basic block. Okay, so it will be asked during the midterm exam, you know. So then let's see the example. Okay. So what is the basic block here in this example? How many basic blocks? By definition. So what is the definition of a basic block? The basic block only includes the target of a branch at the first instruction only, and the branch instruction at the last instruction. So in this example, there are 3 basic blocks, right? Why? This is the basic block because this is the branch instruction, so it's the last instruction. And then this cannot be a basic block. It is because you can find the label here. So this is the another basic block. So basic, and then this is the another basic block. So this is the basic block 1, this is the basic block 2, this is the basic block 3. So there are 3 basic blocks. Okay, in this example. How about this? So by definition, this is the basic block, and this is the another basic block. This is the basic block. Okay. Okay. So you can find that in this example, the size of a basic block is so small. Okay. So I mentioned that if the size of a basic block is large, then we can apply some optimization techniques very easily. But you know, actually in normal applications, the basic block size is so small. So it is because, so actually the percentage of a branch instruction is usually the larger than 20%. So which means that actually the basic block size is usually 4 or 5. So the basic or single basic block includes 4 instructions or 5 instructions on average in a normal applications. So it's very small, so which means that it's not easy. It's not easy to apply optimization techniques inside of a basic block. So that's the problem actually. Okay. Okay, so try to understand about the basic block, and then also try to understand how branch instructions work in RISC-V. Okay, so this is actually a very important part. And then, okay, so let's learn about the function calls. So what is a function call? So this is the example. So also we frequently use a function call in our code, right? So you can find that this is also a function, it's a main function, it's a main function in C. And then actually when a C is executed, C binary is executed, the main function is executed first, right? Okay, so main function is first executed first. So into y is declared, then y is equal to sum. So this is the function call. If the C code encounters a function call, then it executes the statement in a function, a target function. So in this example, it performs A plus B, and it returns the result, the result of A plus B. And then this result is stored in variable Y. So I explained like then. So you can observe that, oh, function call is encountered here. Then this code is executed. So what does that mean? So actually these, so you can think like, oh, these are so C statement, but this statement will be translated into assembly instructions, right? So the instructions, instructions one, two, three, blah, 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 blah. So you can find that some instructions are generated. How about this function part? A function also includes group of statement. It means when a function is translated, then it will include instructions, like the instruction 10, 11, 12, blah, blah, blah. So what does that mean? Actually, instructions are data, right? It's a text data. Then in order to execute instructions, then we need to fetch these instructions from memory. So a function include instructions. So which means if a function is called, which means oh, it jumps to this instruction. Do you understand? So in order to execute instructions in a certain function, then we need to jump to the instruction, the first instruction of this function part. So actually, function call is also it's jump. Okay, and then so actually, we use unconditional branch jump instructions for this function call, right? Because actually, so if you see that this function call, and then if the function call is encountered, then it must jump to the instruction of this function, right? So it's unconditional jump. Okay, so we can implement this function call using jump instructions. So unconditional branches. So function call is also called a procedure call. So you can find the procedure here. Okay, procedure call. Okay, and then so so and then we can classify the function call like the caller and callee. So it means so inside of this main function, the main function, the main is a main function. 왜 이러냐? The main function calls some function, right? So main called some. So main is called caller. So it means that it's calling function. It's calling, okay? It's active form. And then sum is called by a main function. So sum is called the callee. Okay. So in a function call part, I frequently use a caller or callee. Okay. So you can understand that caller is the something that calls a function. Okay. And then callee is the called function. Okay, and then actually it's similar. So you can, so so you know the relation between employer and then employee, right? So employer is the some actively the pay the salary to the employee, and the employee is the employed function, employed person, right? So if we just use the ER, so this is the active form, right? And then if we just use the WE, then it means that it's the passive form. It's also similar to the function call, right? Caller means that it's a function that calls another function, okay? It's active form, and the callee is the called function, okay? So you can find the caller and callee, okay? So in order to implement this function call, then we RISC-V provides the JAL instruction and JALR instruction. So think about this function call. When the main function is executed, and it firstly executes the int y, and then so function is called. So some function is called. Okay, then it jumps to this sum function. Okay, and then this sum function performs a plus b. Okay, and then it returns. So you can find the return statement here. So what is the meaning of a return? So function is complete, and it returns to the next statement of this main function. That's why in C we use return at the end of the function. So meaning is return. So return to the caller, right? So this is the meaning of return. It returns to the next statement. The next statement of function call. Okay, it returns to the so firstly, when a function is called, then it jumps to a function. So it means that it jumps to the first instruction of the function. And if the function is complete, then it returns to a caller. Then what is required? The firstly, to jump to a function, we need to know the target, the other PC, the PC of the first instruction of the function, right? So jump includes the target. But in order to return from the function, we need to know return point. Do you understand? Return, what is the meaning of the return? So if the function is complete, then it returns to the caller. Then it will execute the very next instruction of this function call, right? Then what is the return point? The return point is the PC of this next instruction, okay? So if the function is complete, then it returns to the caller. So it means a processor needs to know return point. It's called the return address. Okay. So so in order to jump to the function, we need to know the target. So it's the first PC of the function, and then we require return address. It's a return point. Okay. So in order to support this procedure, this function, so RISC-V supports the jump and link instruction. So you know this is called the jump and link. So it's a JAL. So JAL has the return address. So this is the destination register, RA. But usually this JAL use RA as the destination register. So it's a you can find the RA is here. So RA is actually X1. This is the ABI name of the X1 register. And then also you can find the target, the label of the function. So this is the target of the JAL. So what is the JAL? So JAL jumps to this target. Okay, the target is the first, the PC of the first instruction in the target function, and JAL stores return address. The return address is the next instruction. So what is the next instruction? So current PC plus 4. This is the next instruction. So this is stored in RA. Do you understand? So I explained how the function is called, and then how we can return from a function, right? So the return address needs to be stored in a certain storage, a certain memory. So this return address is stored in RA, usually X1. Okay, so PC. So if the PC of this JAL is the PC, then PC plus 4 is stored in RA. So this is the jump and link. And then return. So how can we return? If the PC is changed by return point, RA, then we can return from a function, right? The return point is stored. Then in order to return from a function, then this return point is restored. Okay? So PC is updated by RA. Then this is the meaning of return. So in order to support this function, this operation, RISC-V supports the JALR. So JALR, and so then you can find that 0 and RA. So it means that PC is updated by RA plus 0. So this is the offset. So usually, so we can use the 0 because the return address is stored in RA. And then X0 is the destination register, but X0 is not updated. So X0 cannot be changed. So this is the return. Okay. So the function call, so just remember that in order to support the function, so we need to jump to the function, okay, the first instruction of a function, and then we need to return from a function. So in order to support these operations, RISC-V supports JAL and JALR. Okay, so try to understand how the function works in a code. Okay, so I'll stop here. Any questions? Okay, thank you for your attention, and see you in the next class. 감사합니다.